be strong.
For each question. And also, just for your information, you cannot go back, change your answer after you have answered each question. Okay, I think this is one thing I probably have not specifically said. Okay, this is to prevent cheating. Okay, imagine if I allow everybody to go back, you will all sit together and then finish the quiz and go back to check answers, right? And then change all the answers. Okay, no, right? So after you're done with each question, finish, right? Next question, you cannot go back. Okay, again, this is to make sure the integrity of the exam is not broken. Okay, right? Any question on this? Back then, when I was a very young assistant prof, I gave exam when you can go back to change. Everybody scored full marks. Okay, so try and test it. Okay, so no more such things. Okay, so going this way is to make sure that everyone scores fairly, right? You do it by your own credit. You actually know how to answer, and then you score that mark, right? Not by cheating. Okay, okay, but anyway, any other questions on the quiz? Because someone just asked, and then I decided to talk a bit more. All right. Okay. Very good. Okay, so back to Perovskite. Okay, for your benefit, right? I've told the rest. Okay, the quiz. Okay, you cannot go back to change answer. Okay. So once you finish a question, you have to proceed. Okay, so no going back to change answer. Okay, Perovskite bandgap. Okay, we were saying that this Perovskite bandgap is determined by what? The octahedron, right? So the octahedron has what? Halide has the center divalent cation, right? So why is it that when I change this, the bandgap changes? Okay, you can look at this energy diagram here, and you can probably figure out. Okay, so it turns out that let's take the example of this lead halide perovskite. Okay, so this is lead halide perovskite. Now, lead halide perovskite, the octahedron, of course, will consist of an octahedron of lead halide, and turns out that the valence band has properties of the halide. The conduction band, which is the empty band, has properties of the lead 2+. Okay, now if you do the analysis of the valence orbitals of lead 2+ as well as iodide minus, okay, that's what you will be filling. Okay, you will be filling all the orbitals for iodide until 5p6. That means its p orbitals is fully filled with 6 electrons. We know that there's only 3p orbitals, right? So if each of them are filled, then they're fully filled, right? So six electrons in the p orbitals. And again, if you do the same kind of analysis for lead, you will realize that lead 2+ has empty p orbitals. So you'll basically be filling until 6p, and then there's no more valence electrons to fill for lead 2+. Okay, and of course, in a molecular orbital model, okay, you are basically bonding lead and iodide together, right? So when you do a bonding, you form bonding orbitals and anti-bonding orbitals. Bonding orbitals is filled. In other words, this is like your valence band. Anti-bonding orbital is empty. In other words, this is like your conduction band. Okay, and the gap between them is your band gap. Now, if you look at this, the band gap of lead iodide perovskite. If I change, in this case, the iodide to bromide, of course, it's very obvious here, band gap is larger. Okay, but why? Very obvious here, when I change the iodide to bromide, the band gap is larger. That is because bromide has a larger ionization potential. Okay? Bromide has a larger ionization potential. Now, if you look at the periodic table, as you go down the group, the electrons that you're adding to additional shells, basically when you go down the group, you are adding electrons to outer shells, right? Larger and larger shells. Okay. As the shell gets bigger, is it easier or more difficult to remove this electron? Easier, right? As the shell goes bigger, it's easier to remove this electron. And when we say remove, means remove to the vacuum level, right? So if you look at iodide, it's actually very low down the group, right? It's very easy to remove this electron to the vacuum level compared to bromide, right? Bromide is deeper inside. It's harder to remove this electron to the vacuum level. Okay, so this is basically got to do with just analyzing the ionization potential through your periodic table, right? As you go down the group, it's easier to remove electron to the vacuum level. So iodide easier than bromide. So if you then draw the energy levels comparing iodide and bromide, obviously, since bromide is lower down, then the band gap is going to be larger. Okay, you can also change the lead, right? So you just compare this lead iodide and tin iodide case. Same principle, right? Lead is lower down in the group. It's easier to remove electron to vacuum level compared to tin. Tin is higher up. It's more difficult to remove electron. Okay, so energy lower or deeper, if you like. Energy is deeper. Okay, and of course, then if you draw this diagram again, you see that now the band gap has become smaller compared to lead halide. Right? So tin halide has a smaller band gap than lead halide. Okay, so again, it's all to do with ionization potential. Okay. Of course, this is a very crude method of just using molecular orbital drawings to sort of estimate the band gap energy, right? Just a concept. If you really want to do a very accurate calculation, of course, you don't do it this way. Bloch's theorem, right? You use Bloch's theorem, you use a supercomputer, you do all the calculations, solve the Schrodinger equation, and then you get the more accurate band gap, right? But of course, behind it, the concepts is basically okay. Right. Now, because of the fact that you can change the band gap so easily, you can change the halide, you can change the lead, because of this, you can get perovskite with all sorts of band gap, right, and all sorts of colors. Okay, and this is exactly what this group of people did. Okay, so in 2013, this was one of the earlier works. Remember just now I had this paper that shows emitting in all the colors. Okay, that was 2015. So even before that, 2013 already people were trying to determine the band gap of all these mixed halide perovskite, because they can mix iodide with bromide, it mixes with chloride and so on. So they tried out all these variations and they formed perovskite with so many different band gaps. This is absorption curve, right? So absorption curve means that there's no absorption at shorter wavelength, okay, but as you go up to higher energy or shorter wavelength, you start absorbing things. When you absorb, it's an electronic transition from valence band to conduction band, right? Okay, so you can see that the onset of absorption called the onset of absorption. Onset of absorption can be simply fused by switching, in this case, this is a pure iodide, this side is pure bromide. Right? Changing a mixture of iodide bromide from pure iodide all the way to pure bromide, okay, I can actually change the absorption onset. In other words, change the band gap. Okay. And of course, they plotted a very nice graph here. Okay, the lattice parameter changes. Lattice parameter is basically the length of each of these unit cells. Now, obviously, iodide is bigger, right? Iodide is bigger means lattice bigger. Bromide is smaller, right? So lattice smaller. So of course, again, the bigger one will be iodide, smaller one will be bromide. Okay, so you can change the band gap, you can change the lattice parameter, just for information, this kind of phenomena is not just for perovskite. Okay, there are other types of semiconductors that also show quite similar. In fact, same kind of behavior, like gallium arsenide, gallium nitride, indium phosphide. So these are 3,5 semiconductors. 3,5 means 3,5 semiconductors. That if I try to mix, the group 3 elements, or try to mix the group 5 elements, I can get different band gaps. Okay, so there are other examples of this. The only difference is I can do this easily, right? I can just, I just buy another bottle of chemical, mix it. Very easy to synthesize. This is the example for tin. In fact, this is a paper published by my group. Okay, so actually, me and my co-workers, I shouldn't say my group because back then I was still a postdoc. So this was a paper that we published quite early on. Okay, using tin. So we varied the iodide bromide composition, and same thing, right? We can see an absorption onset that is changed for tin halide perovskite. Okay, and one thing extra we did was because I'm very interested in luminescence, so we measured all the luminescence, and very nicely we can get luminescence at different wavelengths. And in fact, if you see for tin halide perovskite, it is quite deep into the IR, okay, because the wavelength of emission is close to 1,000 nanometers. Okay, that's just for your information. There's really not many materials in the world, or not many semiconductors that emit at near infrared or short wave infrared. That means longer wavelength infrared. Okay, so useful for applications. But turns out that tin perovskite has one disadvantage. Okay, so these materials are not exactly very stable, which is why hasn't really gone into industry applications. So stability is a problem. But to show that it emits light and bandgap changes, no problem. Okay. So we've been talking about the lead halide octahedron. So what's the use of those cations at the corner of this unit cell? Right? What's the use of all these cations? Okay, we can't exactly say that they are not useful. Of course, obviously they are there for a reason, to complete the perovskite structure. But really, their role is really as a charge compensating center. Okay? That means they're just there to balance the charges and to sort of finish up the structure. Right? So in terms of the actual involvement in the bandgap, there's actually not much. Okay, I say not much, but not completely zero. Okay, not much effect. So people have done a study on it. Okay, so here by Aperon et al. So they did a study on these 3 cations. So methyl ammonium is what we first introduced, right? Methyl ammonium is quite popular, and then you can change this methyl ammonium to cesium, or you can change it to formamidinium. You can see cesium is smallest, formamidinium is the largest, right? So you have these 3 examples, and when you introduce each of these, you can see that the band gap changes a little bit. Okay, not much, just a little. We're talking about methyl ammonium being in the middle at 1.57 electron volts band gap. And then for mammalium, it's the largest one, having a slightly smaller band gap at 1.48. And the cesium one, 1.73. Small band gap changes. Of course, you'll be asking, okay, why not go even bigger? Or even smaller? Okay, remember Goldsmith tolerance factor? Go even bigger or even smaller, perovskite doesn't form. Okay, so there's nothing to talk about, right? So it's just unstable if it's too big or too small. Okay, so it turns out that this three okay for perovskite structure. Okay, and as I said, they are not directly involved in the band gap. Okay, but what they do is they have an effect similar to pressure-induced changes in band gap. So just for your information, if I now have a semiconductor and I apply pressure to it, okay, then the lattice size changes a little bit, right? Just by squeezing it really hard, right? The lattice size changes a little bit. Even though it's the same material, the band gap will change a little bit. Very simple reason, the orbitals will interact, the electrons will interact a bit differently, right? If you try to squeeze a little bit, the nucleus and the electrons becomes a bit closer together, and of course this changes things, right? And the band gap changes. Okay, so similar as a pressure-induced change. In this case, the cations have different size, okay, slightly different size, so it makes the lattice a bit bigger or a bit smaller, and of course, with this, then the electrons and the nucleus interaction will be a bit changed, and therefore the band gap changes. Okay. And as I said, even larger cations, either it doesn't form a perovskite or it can potentially, I forgot about this, can potentially form 2D layered perovskite, right? If you go really big cations, possible as well. Okay, possible as well. But another possibility is it doesn't form perovskite. Okay, we talk a little bit about this concept called polymorphism. Polymorphism means that the perovskite structure can have more than one types of crystal structure, depending on what. Okay, so I'll do a case study here for this perovskite called cesium tin iodide. Okay, cesium tin iodide perovskite, not the lead version, but the tin version. Okay, this is in a paper that's been published. I believe it's this 2013 paper. So what happens is at high temperature, okay, at high temperature, perovskite is a cubic structure. Cubic structure, you all know what a cube is, right? So that means all the sides A, B, C, they have equal length. Okay, it's just a perfect cube. Perfect cubic structure at high temperature. But as I said, there's this concept of polymorphism. That means it can actually change into another structure if I lower the temperature. So if I lower the temperature, it can form what we call a tetragonal structure, distorted structure. Perovskite, but distorted. Right? Tetragonal structure is where two sides have equal length and one side has unequal length. A equals to B, but not equal to C. But it is just slightly distorted in one of its dimensions. Now, if I cool it even further, it becomes what we call orthorhombic structure. Now, all three sides are not equal. It's no longer, well, of course, it's not a cube. In this case, it's still a perovskite structure, but it's completely distorted in all three dimensions. In all three dimensions, it's distorted. All three sides are no longer equal. And these people also discovered that now if I expose this material to air, it forms a non-perovskite structure. Some people like to say, oh, this perovskite has degraded, right? Degraded. It is no longer a perovskite. Well, in a way, it's true. The perovskite has really changed to something else. They call this the gamma phase. Okay, so it's this just a name for it. It's a non-perovskite gamma phase upon exposure to air. And I think now we understand it a little bit better. It's usually created by moisture. So why air, right? So it's usually caused by moisture in the air that causes it to change to another structure. Right? And if you like, this structure is a 1D double chain structure for gamma. Right. Now I want to use the case of perovskite to illustrate another concept in semiconductor. In a way, we are going back a bit to sort of foundational semiconductor knowledge. Okay, but I think perovskite is a very good example for this. I want to talk about structural disorder in semiconductors. Okay, we all know that say silicon or perovskite is actually a very ordered crystal structure, right? And you all know what a crystal structure is, right? There's a repeating unit with very well defined atomic spacing. The layers are very ordered, right? So the spacing between atoms are very ordered. Now, of course, this is sort of the perfect case scenario. Most of the time, there are many semiconductors that have disorder. Disorder means what? Some atoms are a bit further apart, some atoms are a bit closer together. In some cases, it can be completely disordered. It becomes amorphous. Amorphous means non-crystalline. That means all the atoms do. By the way, you have amorphous silicon, right? So all the silicon atoms are randomly arranged in that solid. Okay? Some bonds short, some bonds long. Okay. So of course, there are some cases in between, right? So there are some semiconductors with a little bit of disorder, not extreme. Okay. So turns out that disorder in a semiconductor can cause changes in, of course, a lot of its properties, right? Especially its bandgap. Now, if you look at this diagram here, so this is the valence band, and then on the right side is the conduction band. Now, if you imagine that every single bond is the same length, very, very ordered, every bond is the same length, you would think that the band gap is very clean. It's a very, how should I say, it's a very sharp transition from valence band to an empty band gap, and then another sharp transition to the conduction band. But when you have a very disordered system, then you would see this red color line here. Where the transition is not so clear. It's a very gradual transition, okay? From conduction band to band gap, and then from valence band to band gap, and then to conduction band. Okay. What's the reason, right? What's the reason for this slope? Think about it. What is the fundamental nature of these bands? It's bonding orbitals and anti-bonding orbitals, right? The bands, at least as we sort of recall, the valence band is basically made up of filled orbitals, right? Filled bonding orbitals, and then the conduction band is basically anti-bonding empty orbitals. Now, if all my bonds are the same length, then I would have a very fixed value for my bonding orbital and anti-bonding orbital, correct? If all my bonds are the same length. Now imagine if I have a case where some bonds are shorter, some bonds are longer, then some of my bonding orbitals will be a bit lower, some of my bonding orbitals will be a bit higher, and so on, right? So I will have a distribution of bonding orbitals and I will have a distribution of anti-bonding orbitals, correct? And this distribution is represented as what? As that slope, right? It's a distribution of states. I now have a distribution of states here. If it's ordered, I don't have a broad distribution of states. I have a very sharp edge of the states. All of them same energy, right? But if I have some shorter bond, some longer bond, because it's disordered, then I have a distribution. So that accounts for that slope. The way it's not a very clean bandgap. What is worse is in a disordered semiconductor, sometimes I get dangling bonds. What is dangling bonds? I'll give you an example. Silicon is supposed to have 4 bonds, right? But in some cases, the silicon only has 3 bonds. That means what? It has some empty, empty space that likes to bond with another silicon, but they cannot, right? For whatever reason, it's on the surface, or because it's so disordered, there's only 3 silicon around it. So there are certain cases where there's a missing bond or dangling bond, and this will show up as what? Localized states. Localized states in the middle of bandgap. And these localized states are basically traps. Right? They're traps that causes, last week we covered this, Shockley red hole recombination, very bad for LEDs. Right? Okay, so this is a problem with this order in semiconductors. Localized state, you don't get a very clean bandgap, you get a distribution of states. Now, basically, I've talked a lot, but essentially it's all summarized in the text here. I'll read it out for you. Okay. Now, what is the implication of this distribution of states? Distribution of states to what? Remember, absorption of light to this electronic excitation is from a low state to a high state, right? So now I have a distribution of energy when I excite electrons from a low state to a high state. In other words, when I excite from the valence band to a conduction band, sometimes I use less energy, sometimes I use more energy. So on. Okay, so there will be a distribution of excitation energy. Okay, so if I have a distribution of excitation energy, it shows up in the absorption curve. Correct? So this is the absorption curve. Absorption curve. In fact, whatever in the y-axis here is the absorption coefficient. Absorption curve. Typically, it's a very sharp line that is expressed by this. This basically an exponential function. Because typically in a very, very ordered system, all my bonds are the same length. The bonding orbital and anti-bonding orbital has the same energy. So most of the time, they use the same energy to excite from the valence band to the conduction band, right? But in a very disordered system, I have a distribution of excitation energy. So this line then becomes blunted. Now this is very useful because now we can mathematically define disorder by looking at this slope. By looking at this slope, how gentle or how steep it is, I can tell whether a semiconductor is ordered or disordered. Expressed by this equation here, okay, absorption coefficient alpha equals to alpha naught e to the power of energy over EU. Okay, so for you might be a bit confusing. Let me explain term by term. Okay, this is just a fitting constant, so we don't care about that. Exponential function, you all know, right? Exponential function. Typically, your absorption curve is an exponential function. Now, the energy of excitation, in other words, is x-axis here, right? Of excitation. Some people might be a bit more used to wavelength, right? It's the same, right? Because of the Einstein's equation, Planck-Einstein equation. Okay, so E equals to hc over lambda. We can basically interconvert energy with wavelength, right? So some people might be more used to spectrum that has a wavelength bottom here. It's the same. Okay, so energy, you can plot it in terms of energy as well. Okay, but anyway, so this is the x-axis, the energy of that excitation. And then you see this red color term here labeled as EU. EU is a fitting constant that tells you how steep this slope is. Has a name for it. It's called Above energy. Named after this guy called Above. Okay, so it's called Above energy, but it's actually a fitting constant to tell you how steep this slope is. Now let's take a few examples, right? If Above energy is small, Above energy is small, exponential curve is huge, right? Correct, is in the denominator. Above energy is small, this exponential function is huge. Correct? So that means what? The exponential rise is sharp. So if EU is small, then I have a very sharp line, something like that. That's for the case of above energy. If above energy is large, then it's something like that. Exponential curve is gentle. Above energy is large. Okay, so that's it. You can see that this is basically related to disorder, right? Remember we were saying when we have a disorder, then it's going to be a distribution of excitation energy, it's going to be a gentle line. Now, if it's very ordered, very crystalline, then it's going to be a sharp line. Okay, so this is ordered. Clear? So yeah, above energy is directly related to order or disorder. Small above energy, order. Large above energy, large disorder. Okay, so this has been done since 2014, 10 years ago. People have already compared. So these guys compared a range of semiconductors, all the way from crystalline silicon to gallium arsenide, cadmium telluride, perovskite, and so on, right? And they also have an example of amorphous silicon, right? Very disordered silicon. It turns out that if you calculate above energy, perovskite has 15 MeV energy. In other words, this EU value is 15 MeV. But to you, it might mean nothing. Right? What's 15? 15 high or small? You have to compare, right? Gallium arsenide, we know, very good semiconductor, 7.5. Okay, so better than perovskite, okay, but not very much better. Crystalline silicon, 11 millielectron volts, also better, but not a lot better. But let's take a look at amorphous silicon. Large above energy for amorphous silicon. Right? So if you compare perovskite and amorphous silicon, you can see a distinct difference. So what this study tells us is that perovskite actually belongs to the family of very ordered semiconductor. That's good. Okay, order is in general is a very good. It belongs to a family of order, not disorder. Okay, simply by looking at the slope, find above energy. Now we want to talk about excitons in perovskite because we learned about excitons last week, right? We learned about excitons in semiconductors. So is it a Frankel exciton or is it a Mott-Wennier exciton in perovskite? Now, of course, I'm not the one to do the study, but others have already done this. Okay, turns out that it's a Mott-Wennier exciton. And if you recall what we taught last week, Mott-Wennier exciton is large. Okay, is over the size of a few lattice spacing. Lattice spacing, right? So large and a large exciton simply because its relative permittivity it has a large relative permittivity. Exciton binding energy, so this one is high, so exciton binding energy is small. When exciton binding energy is small, the exciton is very big. It doesn't bind that electron and hole closely together. The relative permittivity of iodide perovskite is 6.5, and these are based on calculations by these papers. These are actually published results, right? So published results. Of course, there are other papers that have slightly different numbers. As I used to have hey, this paper shows a different value. Yes, sure. I mean, there might be some slight differences between different, but at least in these papers that were quite early on, they studied this and it was right. Okay, and for the bromide perovskite 4.8. Okay, so these are reasonably large relative permittivity, and again, so if you compare to the lattice size, 6.29 angstrom, it's actually a few times larger than the lattice parameter, right? So clearly, this is not a Frankel exciton, not a localized large. Okay, now question. What do you think? By the way, there's a lot of questions that is in this style for your quiz. Okay, true, false. Which one you think is true? Which one is false? And then you get to select, right? Something like this. Okay. Anyway, what do you think are effective strategies in improving the photoluminescence efficiency? You read them yourself. 1, 2, and 3. Then I open up. Just like easier for two people to meet in a small space, right? So now easier for electron and hole to meet in a smaller space. Okay, so if they can meet, then they can recombine, they can give light. Right? So photoluminescence improves. Decrease amount of defects, yeah, certainly, right? So if you can decrease amount of defects, then you get rid of the state, the localized state in the middle, right? So you get rid of what? Shockley red hole recombination. Get rid of it. Decrease photoluminescence. Now, the point that people don't necessarily agree on is increasing the temperature. Okay, so who's right? So increasing is wrong. Do not increase PL, you do not increase photoluminescence by increasing temperature. Reason is very simple. It's all about electrons and holes meeting and recombining. If you increase temperature, it's easier for this electron and hole to go apart, right? There's more thermal energy. The electrons and holes can easily escape each other and not recombine. right? So temperature actually breaks up electrons and holes, breaks up excitons, and that's a bad thing for photoluminescence. One, electrons and holes to be able to meet, combine, they need to be bound into an exciton before they can recombine and give off light. Okay, so in this case, increasing temperature is not useful. Okay, so the next topic that I'm going into is slightly more advanced, a bit more complicated. Don't worry if you cannot follow the math; it's not that important. Okay, I just want you to know the concepts. Okay, so about exciton dynamics or about exciton, how they form, how they recombine. Okay, so of course using perovskite as an example. Now, turns out that it's actually possible for perovskite and other types of semiconductors. It's possible to track excitons. Okay, so it's a bit more advanced concept. But first we go back to how excitons form and recombine first, right? This we already covered, right? Exciton formed by absorbing light. Okay, so if a light is absorbed, the electron is promoted from the valence band to the conduction band. This forms a electron hole pair. If this electron hole pair is coulombically bound, it's called an exciton, right? So this is formation of exciton. Now, this exciton can also recombine, right? This drops back down, gives out light. Okay, this is exciton recombination. Okay, so there's a few situations. There's a few situations. I'll talk about the first situation here. Okay, this is a very simple situation where it just forms and recombines, right? And I can actually write some rate equations. Write some rate equations. You all know chemical kinetics, right? Kinetics A plus B gives you C, and then the rate of reaction equals to K concentration of reactants and so on. Okay, this chemical kinetics. I hope you remember. Chemical science students or chemical engineers should know rate. Okay, so I can actually write rate equation in a very simple way for excitons. It's not exactly a chemical, but you can still write that kind of equation. So for excitation, I can write light as the starting material, as the reactant, generating excitons, right? For the excitation process, this is the product, right? Exciton is the product. Light forming exciton. So reactant product. That's the excitation process. Now, what can happen to the exciton? The exciton can break up and form electron and hole. This is what we call separation process, right? This is the reactant now. The exciton react, separate, form free electrons and holes. This is the separation process. This is the product, right? And then I can write rate associated with it. Okay, so you can see there's a forward arrow, there's a backward arrow. Okay, forward arrow means it becomes free. The backward arrow is the electron and hole coming back together to form the exciton. That's the backward reaction, right? So I can write K1 and K1 prime. And then the exciton can also recombine to give you photoluminescence. Process it, right? Where the exciton is the reactant, photoluminescence is the product. Okay, I can write a rate equation. I can write that this has a rate constant of K2. Okay. So far, this is quite simple, right? These three situations. Now, I want to tell you a situation whereby I don't care about separation. I don't care about this. This situation. So when is a situation where I have no separation? The exciton binding energy is large, right? When the exciton binding energy is so large that it doesn't want to separate. Okay, so in this case, I have a large exciton binding energy, there's no separation. I cancel away this whole thing. Okay, and that makes all my analysis much easier. So I hope to sort of briefly go through the math. But again, don't worry if you cannot follow this. Not the intention for you to study chemical kinetics. Of course, you can do it in other class, but this module not exactly. Okay, so anyway, um, I can write this first reaction, um, first rate equation, dPL dt equals to K2 times exciton concentration. This is a This is a rate equation for this recombination process, right? dPL dt means the rate of change of photoluminescence with respect to time. The rate of formation of PL, if you like, goes to the rate constant kinetics is rate constant K2 times concentration of now with this rate law or with this rate equation, I don't know if you all remember your first order rate law. The first order rate law derivation, you will come up with this equation. In not a chemical kinetics class, I don't want to go through the derivation of the first order rate law. Okay, but just for information, this is the first order. Okay, if I do an integration and so on, I will get this equation where concentration of exciton equals to concentration not e to the power of minus what we call the first order integrated rate law. You can actually search on Wikipedia first order integrated rate law. Now what this means is I can then substitute this equation in here. Okay, and then I get this. As a simple substitution, I substitute the purple equation here. Here. And I still get an exponential function. Now, if you don't care about the math, okay, just looking at this equation, what can I say about the rate of photoluminescence? Just exponentially, right? This is an exponential decay curve. It looks like that. E to the power of negative exponential decay curve. Okay, so that means the photoluminescence will, if I excite it, the photoluminescence will decay exponentially over time. Okay, and if my material, if my semiconductor has a strong exciton binding energy, this is what I expect to see experimentally. I excite it, the photoluminescence will decay exponentially over time. And just for your information, in case you are thinking this happens in terms of seconds or I don't know minutes, no. Okay, this happens extremely quickly in terms of nanoseconds. Okay, so you need to have a very sophisticated tool called TCSPC, which actually I have one in my lab, but there's other labs that have it as well. Okay, so this actually tracks photoluminescence over time. Okay, and very very short time, nanoseconds or hundreds of nanoseconds, very quickly. Okay, and by looking at this, then I can tell, oh, this semiconductor probably has a large exciton binding energy, right? So this is case one, large exciton binding. Okay, this is simple enough, but if you think it's complicated, that's worse. What happens if it has a small exciton binding? In the case where it has a small exciton binding energy, separation can happen. Okay, so in the case of a low exciton binding energy, equations, this chemical kinetic formula still applies. Okay, but this case, I cannot cancel away the separation anymore, right? So all of them are now valid. Okay? So all of them are now valid. And the excitation, the separation, and then the recombination, they're all valid. Okay, which means the analysis is now more difficult. Okay, now I hope you briefly follow through the math. Okay, I'm going to talk about. But don't worry if you can't. Right. So the first equation that we write is actually the same as what we had in the last class, right? L d P equals to K times concentration. This is basically the formula for the last step, right? The recombination. Okay, we can do for let's do it for this. It's the rate of formation or the rate of change of exciton concentration. What can cause a change in exciton concentration? Right. Number one, excitons can form from recombination of electrons and holes, or the meeting of electrons and holes. Meeting of electrons and holes from exciton. So that's basically a backward reaction. The exciton can be destroyed in a forward reaction. Form free electrons and holes. And the exciton can also be destroyed by forming PL. So if you think about it, there's actually three processes, right? That can cause exciton concentration change. So where are the three processes represented in this equation? Now, you can see that in this equation I have minus K1 times concentration of, that is the forward reaction here. Okay, because that forward reaction will deplete exciton concentration, so it's a minus. The reactant is exciton. I have a minus K2 as well. This reaction here. Because forming PL actually depletes the reactant. I can actually keep bonds by changing it to PL. So that's that accounts for minus K1 and minus K2. But I can have a positive here plus K1 prime E squared. That is this reaction. K1 prime is a backward reaction. It is positive because it contributes to the increase in exciton. And the rate is related to concentration of electrons and holes. Then why do you see E squared here? Shouldn't it be E times H? Think about it, the concentration of E is the same as the concentration, right? So E times H is the same as E squared. Okay, so that's why you get E squared. So now I have written two equations. Bear with me, I'll write the third equation. I can write dE dP that's the rate of forming electrons and holes. Okay, what can I do to form electrons and holes? I have K1EH. That means the forward reaction here involving EH can create electrons and holes. So therefore, it's a positive value, right? But I can also deplete electrons and holes. So that's why there's a minus value here, which is the same, which is that's why it's a E squared. So I've now written these three equations. Okay, in a way, that's not the end of the story, but I sort of want to just explain to you how to form these three equations. And of course, if you are very interested in the science and the math behind it, you can go home and try to solve it yourself to come up with that final two equations. Okay, you're welcome to do so. Okay, but I formed these three equations for you, just for you to see how to start, right? And then later on, if you want, you can solve it. Okay, but I want to tell you now. I want to jump to the conclusion. I want to go to the math, not the aim of the module. So you can solve this. You can solve it by assuming that the EH is zero. So this is basically what we call a steady state approximation. Probably remember it a little bit, for your chemical kinetics module. So if you write the EH equals to 0, then you can solve it. You can solve it. You form these two equations. Now I want to tell you that these two equations is what you can track experimentally. And then you can see if whatever data that you have fits these two equations. If the data you have fits these two equations, then you can prove that yes, my semiconductor has a small energy. Okay, if it fits this. What experiments do I run? Okay. Same as before, I can run TCSPC. Benefit of those not familiar. Uncorrelated single photon counting. Okay. You can search it up. It's not part of the module. Don't worry. Okay, but this is basically a time resolved photoluminescence study. Okay, I can then measure the rate of change of PL. Again, nanoseconds, right? Within nanoseconds, decay curve. That decay curve should not be exponential decay anymore, right? That decay curve should follow this. The information is no longer exponential. Which is not exponential decay. Okay, so it's different from last slide. Last slide is a exponential decay. All right. So that's time resolved photoluminescence. Now there's another technique called transient absorption spectroscopy. For students who are in the group of Prof. Xu Qinghua, okay, you will be very familiar with this. Transient absorption spectroscopy. This measures the concentration of excited state over time. Okay, so that means I can actually measure, like, what's the concentration of electrons and holes in my semiconductor over time. This happens very quickly. Again, we are talking about nanoseconds. Okay, we can track the presence of these species, electrons and holes, within the semiconductor over time by measuring their absorption. That's what we call a transient absorption spectroscopy. It measures the concentration of excited time, and this should follow this equation here, the purple color one, which is why I color coded. Okay, but the green color line, okay, photoluminescence equation. The purple color line is the purple equation. Okay, so for those of you who in future, during your PhD, you want to study, whether or not your semiconductor is a high exciton binding energy or low exciton binding energy, how it behaves in terms of recombination. You basically study these equations and see if it fits the curve. And as I've said, this was actually an ex-colleague during my PhD. They actually plotted these curves, okay, doing the experiments, the time resolved photoluminescence, as well as the transient absorption spectroscopy. We did the experiment, and you see the experimental data as all the dots. And this plot, all the dots. And then they fitted the lines, okay, for these equations. And they show what? They show that perovskite has a low exciton binding energy, and it undergoes what we call a bimolecular recombination. And by the way, what is bimolecular recombination? This is bimolecular recombination. Of course, you'll be asking, okay, why is it called bimolecular recombination? Because it requires the meeting of electrons and holes. You need two things to come together to form PL. You need electrons and holes that separate and then come together to give you photoluminescence. Whereas previously, you already have an exciton. Now this is called monomolecular recombination. Okay, so if you want to separate between these two cases, monomolecular or bimolecular recombination, you have to use these techniques, transient absorption spectroscopy. You have to use time-resolved photoluminescence, plot the graphs, fit the line, and you find your answer. Okay, so I think I want another break, another hour. So let's have a break, and in 5 minutes' time, we'll resume.